Hello, Honors Algebra. Mr. Lawrence here, and this is going to be your Chapter 9 review, and there's the last section of Chapter 8, real easy stuff. It's going to be a long review. I may end up splitting this up into two videos. I'm going to see how my time goes, and if the first one goes more than like 15 or 20 minutes, then I'll definitely just, stop it there and then let you know, hey, look for part two. Um, that way you can watch the first part or the second part. You don't have to watch the whole thing if you don't need to. Or if you need to watch part of it once, it might be easier for you to do if you only have to scroll through half of it as opposed to the whole thing. All right, so we're going to start off in the end of chapter 8. And remember, for doing exponential growth or decay problems, our formula was A equal P times the quantity of 1 plus or minus R to the power T. Remember that T has to be in years. Okay, R is the rate as a decimal. In other words, you take the percent and you divide by 100. So it'd be the percent divided by 100. That's how you get R. 1 is there so we don't have to like add things over and over and over again. P is the principal or the starting amount, and A is the amount after T years. So in this first example here, we have an investment of $3,200. That's our principal. Has been growing at a rate of 3%. So R would be 3 divided by 100, which is 0.03, right? So that's going to be R, okay? And we don't seem to know T yet, but when we come down here, part A says what will it be its value? What will be its value 10 years from now? Well, there's your T. Okay, so we just do a simple plug and chug, really. I'm not sure why this problem would give anybody difficulty. Anybody as smart as those of you listening, that is. The rate is growing, so I'm not going to use the minus. Okay, and then at this point, I can just go to a calculator and get my answer. Give me 1 second here. 3,200 times the quantity of 1.03, and that will be to the 10th power. And it looks like we're going to have about $4,300.53. So let's get that down there. $4,300.53. And there you go. It's that simple. All right. Now, what was its values 6 years ago? Well, it's the same problem, except the time has changed. We're assuming this investment has been going on for a while, at least 6 years. It's still 1 plus 0.03 because the investment has been growing. However, we're going back in time, and so the exponent is -6. And so I just can go to my calculator at this point and change the t to -6. And it looks like I'm going to get about 2679.95. So that would mean that A is going to be approximately 2679. And then it's about 95 cents, and that is a rounded answer. I came up with a decimal of 0.949621, and since we're talking money, I rounded to the hundreds place, and there you go. All right, let's look at another example here. This time we'll look at a decay example. We have a town that has been losing people at a rate of 1.4%. Well, that's R. Of course, I'm going to do 1.4 divided by 100, and so then R will actually equal 0.014. Okay, today the town has 50,000 people. That's my principal. And it looks like what will the population be in T years? 15 years. Well, there's my T. So I'm just going to go A equals 50,000 times 1 minus 0.014. And that'll be to the 15th power. So A is going to equal, now I got to be careful here on my rounding because I'm talking people, I'm not talking money. So let's see what kind of answer I get. 1 minus 0.014, and we're going for 15 years. And so it looks like there's going to be about 40,469. Oop, where'd my thing go? 40,469 people. Okay. The decimal came out to be 40469.11699. And this doesn't really make sense as a part of a person. And so therefore I rounded down on it. Even if it had been like a 0.98, I probably still would have rounded down because I didn't have the whole extra person. Okay. What was the population 12 years ago? Well, it's the same problem. 50,000. The R is negative, not because we're going back in time, because we're losing its exponential decay. The time is negative. And so I just go to my calculator and change that to a negative 12, the exponent, and I get that A is approximately 59,217 people. Okay, I'm not expecting to do a whole lot more on that. Pretty simple stuff. Let's get on to the next section. All right, we got into naming polygons, right? And remember, monomials have one term. Like, for example, 5x to the fourth is a monomial because it has one term. A binomial has two terms. Sometimes it looks like 2x plus 1. It could look like 6x to the fourth minus 2x to the fifth. Trinomial would be three terms. So if I had a 5x squared plus 2x minus 4, that would be a trinomial. Polynomial means just more than four terms. All right, a constant is just something that doesn't change, a number. Okay? Linear would be 6x plus 1 or 4x minus 1. Because if I stuck a y in front of those and turned it into an equation, y equals, I would get a line when I graphed it. You could even do like 1/2 x plus 2. They're all linear. They'd all produce lines. Quadratic, the highest power has to be 2, and we've been working with quadratics, and we're going to spend a lot of time. Next chapter will be all quadratics, and we're actually going to learn about graphing them. Okay, that's quadratic. All right, quadratic could be a trinomial, like when we factor, like a perfect square trinomial. Those are quadratic. Cubic, the highest power is 3, so if I had x plus 2x squared plus 3x cubed, see the highest power is 3, that is cubic. And when the highest exponent is a 4, then we say it's quartic. And, you know, it could just be like 10x to the fourth, a monomial, a quartic monomial, or it could be, you know, a binomial, or a trinomial, or a polynomial for that. All right. Now, typically, if you're going to name them both at the same time, I would say the degree and then the number of terms. So, for example, this is a cubic trinomial. There's a quadratic binomial. There is a linear binomial. There is a quartic binomial, etc. All right, so that's pretty simple stuff. Gotta just stick it on a brain cell. Adding and subtracting. Now remember, adding and subtracting is all about combining like terms. And I'm going to see there's a 5x squared here, but there is no x squared term there. I have a positive 2x, and I have a positive 3x. Okay, I also have a negative 3 and a negative 5. All right, so I'm going to combine my like terms together. My 5x squared, which is by himself, my kind of dark yellow things that have been highlighted, and then my orange ones, minus 8. And by the way, I have a quadratic trinomial for an answer, right? Okay, now one thing many of you will make a mistake on is like problem number 2. You see this negative here? Who does he belong to? This entire quantity. I need to distribute him. Now, I don't like to rewrite the whole thing. Kind of lazy. Certainly you can. I like to multiply by -1 all the way through the problem. Okay, and then I go to my highlighters, and let's see, I've got an r cubed. I don't have any other r cubes. I've got a -3r squared, and I've got a -r squared. There we go. And then, oh, I can probably just go right here. I've got a -7 and a -4. I'm going to do these in a different color so I don't accidentally put them together. I've got an r cubed all by himself, and I have a 14r by himself. So, r cubed, looks like I've got -3 plus 1r squared, so it'll be -2r squared. Only have one r term, and there's 14 of them. And then I have -11. Okay, and by the way, my answer would be a cubic polynomial, right? Okay, let's see here. All right, I think I am going to cut this video short, do it in 2 pieces, and that's okay. We'll get to the distributing and foiling, and then we'll be able to stop this video and make a second one. Okay, so let's just do some simple distributing here. We're going to multiply 3x by the entire quantity, right? Distributing is kind of like passing out suckers to everybody in the row. You know, if I'm going down my first period row where I have Marion and Mitch and Daniel and then Max, you know, if I walk down and give Marion a sucker, that'd be like doing 3x times 5x to the 6, which would be 15x to the 7. And then I give Mitch a sucker. That's the next term. I'm calling Mitch this term. See, this was Marion, this one's Mitch. I'd get a 6x cubed. And then all of a sudden I stop and I forget to give Daniel a sucker. And then I give Max a sucker. Well, Daniel's upset. I didn't do something right. So I don't want to do that. I want to make sure I pass out suckers to everybody in the row. And so a 12x squared. And there you go. I can't combine any of these. I hope Kelsey's listening to this, because one mistake I've seen her do is just try to ram all these together. These are not like terms. Okay, that's an x to the 7, that's an x cubed, that's an x squared, and that's a plain old x. They don't go together. Okay, a FOIL problem. Remember, first, outer, inner, last. To do my firsts, I'm going to get 30x squared. To do my outers, I'm going to get a 25x. To do my inners, I'm going to get a -36x. And then my lasts gets me a -30. And then I'm going to combine like terms. I've got 30x squared minus 11x minus 30, and I'm done. And by the way, my answer is a quadratic trinomial, right? Okay, now some of you are going to get a mistake on here. I'm going to do this one real quick, and I want you to tell me what the mistake is. Did you catch that, Jeremy? I didn't FOIL. I just squared what I saw. What I'm forgetting is that this 2x plus 1 as a quantity squared really means 2x plus 1 as a quantity times 2x plus 1. And so when I FOIL, I'm going to have outers and inners. Yeah, if you just square the first term and last term, you don't get the outers and inners. It's a FOIL problem in disguise. So now I can FOIL for x squared. Looks like I can get a plus 4x and then a plus 1. And notice that answer is very different than the other one. Okay, I'm going to pause the video here. The next, I'll give you a little sneak preview. We're going to be getting into the factoring and some word problems and solving. All right, so this was the end of part 1 of the review video for Chapter 9. Mr. Lawrence signing off.